So we are going to be using this a lot. Actually, we'll be using just two. So there are 4 compound angle identities. First one is when you have, there is addition of 2 angles and you have to find out the sign of that. So this is sine of x times cosine of y plus cosine of x times sine of y. Then you have sine of x minus y. So it's the same expression just with the negative sign. Okay.
Got it.
So same expression just with the negative sign. Then third, we have cosine of x plus y. This one is cosine of x times cosine of y minus sine of x times sine of y. And then we have cosine of x minus y. This is again the same expression, just with the plus sign instead of the minus sign. These are the 4 compound angle identities. Have you seen them before?
No, these are actually kind of new. I've never really seen them in this maybe format. Interesting.
Okay, so maybe we can do the proofs of these identities as well, but these identities have a really long proof. So maybe we'll do it.
Maybe not the proof, maybe like a problem involving each one.
Yeah,
right?
yeah,
I don't know.
we can do that. But right now, the reason I'm writing these identities is because these identities I will be using to prove the other identities that we have been using in our last couple of classes. Yeah. So majorly I'm going to be using this one and this one. So if you remember, let me go to the next page.
Oh yeah, quick thing.
Yeah.
Will these like proofs and identities and everything be important for the next for this coming semester, like for my class?
No, not at all, not at all.
Okay.
But I am like, I never give my students just an identity that here is an identity that I'm using without telling, how this came up in the first place. Because otherwise
Okay.
you'll be just cramming it up. So
No, I got it. I was just wondering.
yeah. Okay, so you remember we used this identity. Again. Wait a second, where is this? Yeah. Okay. We have been using this identity sine 2x, which is twice of sine x times cosine of x. This is a very useful identity in trigonometric integrals. We have been using this a lot in our previous questions, right? So this comes from the previous compound angle identities. So we will do its proof, okay? So let's say we have sine 2x. So I can write this as sine x plus x. Can I write this? 2x as x plus x? Right? I can write this, right?
Yes.
Yes. Now I will apply the what was that? Compound angle identity. So sine of x plus y. You remember the expression? Sine of x plus y is sine of x.
Sine of x minus
Sine of x
I'm
times
sorry, sine
cosine
of x
of
times cosine of y minus,
plus.
so plus, why am I, oh, sorry, plus cosine of x times sine of y.
Yes. So we will use this identity to expand this sine of x plus x. Okay. The good thing is here x is x and y is also x. So this becomes sine of x and cosine of x, because my y is basically x, then plus cosine of x and sine of x. So this becomes, so you have 2 of sine x cos x. So this becomes 2 sine x cos x. And that's basically your right hand side.
Oh, okay. Interesting. That makes sense.
Okay. So this is the proof of this identity. Now let's do cosine of 2x. Now this cosine has actually many forms.
Oh yeah, it has a lot.
Yeah.
Like 1 minus sine 2x, I think? Or sine
Yeah.
squared x.
Yeah, it has many forms. So I'll write all 3 of them. So we have cosine number 2. Cosine of 2x is, first of all, it is cosine square x minus sine square x. Then it is also 2 times cosine square x minus 1. And it is also 1 minus 2 times sine square x. It has these 3 forms. Okay. So again, we will be using the compound angle identity. So this cosine of 2x, I will write it as cosine of x plus x. Okay. And then we will expand it as per the compound angle identity. So it was cosine of x plus y was cosine.
Cosine of x plus y is cosine of x times cosine of y minus sine of x times sine of y.
Yes, sine of x times sine of y. Okay, so we'll use this. So this becomes cosine of x times cosine of y, which is basically x, minus sine of x times sine of y, which is basically sine of x. So this is cosine square x minus sine square x, which is the first form, which is this one. So if this is 1, this is second, this is third. So this is the right hand side of the first one. Okay, now think about it. From this one, can you reach the second part and the third part? Let me give you a hint. We will be using this identity. Cosine square x plus sine square x equals to 1.
Reminds me of the Pythagorean theorem.
Have you seen this one before?
Yeah.
Okay. So we have to use this one.
I think we take both of them.
We will use this one. So tell me, what will be the value of cosine square x from this expression?
1 minus sine squared x.
Exactly. So from here, cosine square x is 1 minus sine square x. So I'm going to replace cosine square x by 1 minus sine square x. So 1 minus sine square x and minus this one. So you get 1 minus 2 sine square x, which is the right hand side of the third form. See, this is the right hand side of the third form. And to get the second form, what should we do? From this step, now instead of writing cosine square x in terms of sine, this time we will write sine square x in terms of cosine square x.
Okay.
So I'll write cosine square x as it is, and sine square x is again 1 minus cosine square x. So we do that, 1 minus cosine square x. We distribute the negative sign inside. So this is negative 1 plus cosine square x. So we can add these two cosine square x. So we get 2 cosine square x minus 1.
Minus 1.
Which is the right hand side of the second form.
Oh.
So this is the proof of the three forms of cosine. Let me just highlight it. And this is actually, I love how I can write cosine 2x in these three ways. It's really helpful when we are doing the integrations.
Oh, yeah. Really is.
Yeah, it's like a lifesaver. Okay, let me know when I can move to the next screen.
Yes.
Okay. We have done sine 2x. Okay, now there is also one identity that we have been using, which is number 3, 1 plus tangent square x. What is this equal to?
1 plus tangent squared x. 1 plus tangent squared. I know this. Give me a second. If you like. It doesn't equal secant squared x?
Yes. This is secant square x. Okay. Now we'll try to prove that. This one is really simple. So I'm going to start with the left hand side. 1 plus tangent square x. I'm going to write it as 1 plus, and we know that tangent is actually the ratio of sine and cosine. Exactly. So I'm going to write it in the form of the ratio of sine and cosine. So this becomes sine square x over cosine square x. Okay?
Right.
Then I'm going to take the LCM. So this is cosine square x. This is cosine square x plus sine square x. And what is cosine square x plus sine square x?
Isn't that 1?
Yeah, exactly. So that's 1. So 1 over cosine square x. And what is 1 over cosine square x?
Isn't that secant?
Yes. So I'll just write the reasons. Here we have used that cosine square x plus sine square x is equal to 1. We have used this. And here we have used that 1 over cos x, cosine x is secant of x. They are the reciprocals of each other. See, trigonometry is not that bad after all. We use these two, and here we use this one. This is the most important identity, the sum of cosine square x and sine square x, this one.
I got it.
Okay.
Mm-hmm.
We can also do the proof of this one, cosine square x, sine square x, if you want.
Cosine squared x and sine x?
Mm-hmm.
I think I got it, honestly. I know that formula really well because it's basically the Pythagorean theorem.
Yes, exactly.
So
Okay.
I'm not worried about that.